Welcome to this deep dive into the fascinating chemistry and physics behind the perfect Neapolitan tomato pasta sauce. This simple sauce is actually a complex colloidal system where science meets culinary art through emulsions, Maillard reactions, and polymer chemistry. Before we dive into the chemistry, let's understand what makes this sauce a perfect example of food science. Tomato sauce is remarkable because it contains both water-soluble compounds like sugars and acids and oil-soluble flavor molecules. Normally oil and water separate due to their different polarities, but in a good sauce, they remain mixed for hours. The secret to this stability lies in understanding colloids, emulsions, and natural emulsifiers released during cooking. Natural emulsifiers like pectins and proteins act as bridges, with one end attracted to water and the other to oil, stabilizing tiny droplets. Let's examine what happens when we simmer tomatoes for extended periods at controlled temperatures. Fresh tomato cells are rigid structures. Their walls contain pectin polysaccharides and cellulose fibers that maintain cell integrity. Here, we see an intact tomato cell with its rigid pectin and cellulose matrix forming a strong structural network. When we heat tomatoes to 85 to 95 degrees Celsius, enzymes and heat energy begin breaking down pectin chains. Pectin chains contain 100 to 1,000 galacturonic acid units linked together in long polymers. Through hydrolysis reactions, water molecules break the glycosidic bonds connecting these sugar units, releasing shorter chain pectins. Long pectin chains break into shorter fragments, which are more soluble and better at stabilizing emulsions than intact long chains. Extended simmering for 45 to 90 minutes provides optimal pectin release without complete degradation. You might ask, why does overcooking make the sauce watery instead of thicker? The answer is that excessive heat completely hydrolyzes pectins into very small sugar molecules that lose their thickening ability. Now let's explore the thermodynamics and kinetics of forming a stable oil-water emulsion in our sauce. Olive oil consists of non-polar triglyceride molecules, while tomato juice is mostly polar water with dissolved ions and sugars. The Gibbs free energy of mixing equals enthalpy of mixing minus temperature times entropy of mixing. For oil and water, the enthalpy of mixing is positive, meaning it requires energy input, and is thermodynamically unfavorable. The interfacial tension between pure oil and water is about 20 to 30 millinewtons per meter. In an emulsion, tiny oil droplets are dispersed throughout the water phase, creating a huge surface area between the two phases. The energy required equals interfacial tension times surface area. If we divide 1 milliliter of oil into 1 micrometer diameter droplets, we create about 3,000 square centimeters of interfacial area. This requires about 0.06 joules of energy, which seems small, but is significant at molecular scales. Released pectins adsorb at the oil-water interface, reducing interfacial tension to just 5 to 10 millinewtons per meter. The Maillard reaction is responsible for creating hundreds of flavor compounds when we gently fry garlic and onions. The Maillard reaction begins when amino acids from proteins react with reducing sugars like glucose and fructose. First, an amino acid combines with a reducing sugar to form a Schiff base through condensation. The Schiff base then rearranges to form an Amadori product, which is the key intermediate in the reaction. From Amadori products, hundreds of different flavor compounds branch out through multiple pathways, creating pyrazines, furans, and other aromatics. The optimal temperature for Maillard reactions in garlic and onions is 140 to 165 degrees Celsius. At this temperature range, we form highly desirable compounds like 2-methyl-3-furanthiol, which has a meaty, savory aroma. Reaction rates follow the Arrhenius equation, where rate constant K equals A times E to the negative activation energy over RT. The activation energy for Maillard reactions is approximately 80 to 120 kilojoules per mole. Now you might wonder, why does overbrowning create bitter flavors in the sauce? The answer is that temperatures above 180 degrees Celsius form acrylamide and complex melanoidin polymers. Acrylamide specifically forms when the amino acid asparagine reacts with reducing sugars at temperatures exceeding 180 degrees Celsius. This pathway produces acrylamide, which contributes bitter and harsh flavors, while also being a potential health concern. Melanoidins are large, brown, nitrogen-containing polymers that contribute color, but add undesirable bitter notes when formed excessively. Let's examine the specific flavor compounds generated when we cook garlic and onions properly. Allicin from garlic has an incredibly low detection threshold of just 0.01 parts per million, making it extremely potent. When garlic cells rupture, the enzyme allinase converts alanine into allicin, the compound responsible for garlic's pungent aroma. When we apply gentle heat, allicin transforms into more stable compounds like diallo-disulfide and ajuine. Fresh-cut onions produce propanethyl S-oxide, the infamous lacrimatory factor that makes us cry. Cooking converts these harsh sulfur compounds into sweet-smelling thiols and sulfides through thermal decomposition. Heat transforms harsh sulfur volatiles into pleasant sweet compounds, changing the flavor profile from sharp to mellow. Simultaneously, sugars in onions undergo caramelization at temperatures between 110 and 180 degrees Celsius. Sucrose first breaks down into glucose and fructose, which then polymerize into complex caramel compounds. Now we reach a crucial step that many home cooks overlook, adding starchy pasta water to finish the sauce. As pasta cooks, it releases starch molecules, primarily amylose and amylopectin, into the cooking water. The concentration of starch in pasta water reaches approximately 2 to 4 grams per liter. Amylopectin has a highly branched structure with many glucose units radiating from central chains. Amylose, in contrast, consists of long, unbranched chains of glucose molecules linked end to end. These starch molecules serve dual purposes as both emulsifiers and thickeners in the final sauce. The mechanism works because starch molecules adsorb at the oil-water interface, providing steric stabilization. Viscosity follows the Einstein relation, where ETA equals ETA 0 times 1 plus 2.55 plus 14.15 squared. Here, phi represents the volume fraction of dispersed particles, including both oil droplets and swollen starch granules. Adding pasta water increases phi from approximately 0.15 to 0.25, significantly boosting viscosity. This graph shows the nonlinear relationship between starch concentration and sauce viscosity, demonstrating why even small amounts matter. Finally, let's understand the physics of why properly made sauce clings beautifully to pasta strands. The contact angle between sauce and pasta surface determines how well the sauce wets and adheres to the pasta. The Young equation states that cosine theta equals gamma SG minus gamma SL divided by gamma LG, where theta is the contact angle, and the gamma terms represent interfacial tensions between solid, liquid, and gas phases. Here we see a sauce droplet on pasta with contact angle theta determining how well it spreads and adheres. For optimal coating, we want a contact angle between 30 and 60 degrees, indicating partial wetting. If viscosity is too low, theta approaches 0 degrees, and the sauce simply drips off the pasta. If viscosity is too high, theta exceeds 90 degrees and the sauce remains separate, failing to integrate. The combination of starch from pasta water and pectin from tomatoes creates the perfect viscosity range. Let's quantify emulsion stability using the concept of creaming velocity and coalescence rate. Stokes' law gives us the creaming velocity. V equals 2R squared G times the density difference divided by 9 ETA, where R is the droplet radius, typically 1 to 5 micrometers in a well-made sauce. Smaller droplets cream much slower because velocity depends on radius squared, so 5 times smaller means 25 times slower. For typical values, radius equals 2 micrometers, oil density 920 kilograms per cubic meter, viscosity 0.5 Pascal seconds. This gives a creaming velocity of about 8 times 10 to the negative 10 meters per second, or just 0.07 millimeters per day. This extremely slow creaming velocity means the sauce stays stable for days when stored properly in the refrigerator. Compare unstable sauce with large droplets creaming quickly to stable sauce with tiny, well-dispersed droplets. Temperature control is absolutely critical for achieving the right balance of reactions in your sauce. Different chemical reactions have vastly different activation energies, meaning they respond differently to temperature changes. This graph shows how pectin breakdown, Maillard reaction, and degradation reactions all accelerate differently with temperature. The sweet spot is 85 to 95 degrees Celsius for simmering tomatoes and 140 to 165 degrees for frying aromatics. As a rough rule, reaction rates approximately double for every 10 degrees Celsius temperature increase. This means cooking just 10 degrees too high can lead to overcooking in half the expected time. The pH of your sauce dramatically affects both pectin behavior and flavor compound stability. Fresh tomatoes naturally have a pH between 4.2 and 4.6, making them acidic. Pectin gelation works optimally at pH 2.8 to 3.5, which is more acidic than fresh tomatoes. Low pH protonates the carboxyl groups on pectin chains, reducing electrostatic repulsion between chains. At high pH, negatively charged carboxyl groups repel each other. At low pH, protonation removes charge, allowing chains to associate. Many cooks add a small pinch of sugar to balance the perception of acidity without changing pH significantly. Let's walk through the complete process, understanding how each step builds on the previous chemistry. Step 1. Gently fry sliced garlic and diced onions in olive oil at 140 to 160 degrees Celsius. This temperature builds hundreds of desirable Maillard compounds without forming bitter burnt flavors. Step 2. Add crushed tomatoes and simmer for 60 to 90 minutes at a gentle bubble. During this time, pectin breaks down into soluble fragments, water evaporates, and flavors concentrate intensely. Step 3. Add salt, fresh or dried herbs like basil and oregano, and adjust seasoning to taste. Step 4. Add your cooked pasta along with 50 to 100 milliliters of starchy pasta cooking water. Step 5. Toss everything vigorously for 30 to 60 seconds to create the final emulsion. Here we see the complete process, from cooking garlic and onions, adding tomatoes, to finally combining with pasta and starchy water, creating a harmonious blend of flavors and textures.